Okay, so this is problem 38 out of chapter 18 in the Boylstad book, version or edition 13. So this is figure 1895, and what we're going to do here, we have a delta and a Y circuit. So what we're going to have to do is use the reduce approach to reduce this into a single impedance. Then we will be able to determine the total. We'll be able to determine the total current I up here. And then we we could go back through and determine individual currents if we want. Okay, but looking at this circuit here, we have a delta with capacitors and resistors, and then we have a Y with inductors. And so what we need to do is we need to convert and simplify. And so, as I've stated before, one of the first things that we should probably do is simply come in here and kind of label these. So I'm going to label the nodes. So I'm just going to kind of come up here and label. This is and also color code these so that we can kind of track these points. Okay. And so I'm just choosing some different colors here so we can kind of keep track of these. And then we're going to come in here and I'm going to create, I'll call this point C, and then point A, and point B. Okay, so I'm just kind of labeling and color coding these to match. So up here is point A, and here's point B, and here is point C. Okay, and so so these 3 points, A, B, and C, are actually all touching. Okay, so one option to try to do this might be to take the delta and make it a Y. So if we were to do that, we might try to come over here and take point A. Now it's not color coded, but I'm just going to try to sketch this. So we might try to take point A and make that into a Y, and then we would have this circuit going here, and this would be point B. Okay, so that would be point B, and then this over here would be like point C. Okay, so if we were to do that, this again, this up here would be point A. I'm just coloring it now. There's point A, and point C is this green. Okay, so this is point C in green here. So these points, this is point C, this would be connected. And then point B would be connected. And point A would be connected. All right. So then if we were to do something like that, then we could kind of maybe come in here, and that would replace the delta circuit. Okay. So now we would have a Y, but this Y is in parallel with this Y. All right. And when you first look at this circuit, you may think that this center point here, so this point right here, is the same as this point. Okay. However, that is not true. Okay. So these 2 points are not the same point. So you probably, so if you did that, then you would have to combine these two, which are in parallel. But see, this point is touching point C, and this is touching point B, so those really aren't in parallel. And so the circuit actually gets more complex if you try to take the delta and make it a Y. So the best strategy would be to take the Y and make it a delta. Okay, so I'm just removing this circuit here. Okay. All right, and so what we're going to do is we're going to cut out the Y. Okay, so I'm going to cut out the Y, and we're going to bring that over here. Okay, and then we need to then make that a color. We need, so this is point A here, so A is connected up here, and this is point C over here, so point C is connected, and this is point B is connected over here. All right, so we have the Y with the inductors, and we have the delta with a capacitor and a resistor in series. Okay, but so what I'm going to do here is create a delta inductor circuit like so. Okay, but what we know here is we know that this node right here is node B, this node here is node A, and this part of node C. So we know those values there. All right, and so now this is a balanced Y, and so when we go to when we want to go to a delta, from a Y, we need to basically triple the values. All right, so this is 3, so this is going to be a 9, and a 9 ohm. Okay, so that then allows us to replace this and Y connection with a delta connection. Okay, so we're coming from point A here. If I'm going to redraw this delta back in line with the first delta. So we're going to come up here. We're coming from point A, and we have this inductor circuit here, which is 9 ohms, from point A to point B. So that is this part right here, from A to B. And so I've drawn that in there. So I'm going to remove that section. Okay. And then I'm going to, from point A to point C, there's then the inductor. So we're going from A to C. Okay. And there's another 9 ohm. And then we're going, so that was this section. And then I have from C back to B is an inductor of 9 ohms from C to B. Okay. All right, so that gives us all of those portions. Okay, so I don't really need these extra traces here. So I'll just remove all of this. All right, so now looking at the circuit here, we have this circuit where the capacitor and the resistor are in parallel with this inductor. So if we come back to, like, say, point A, okay, so point A, we're coming down here, and we have the circuit where there's a capacitor and a resistor in parallel with an inductor. Okay, but coming in point A in the other way, we have the inductor, and then we have the capacitor and the resistor. Okay. All right, so this point right here is actually right here, so that's actually node C. So this here is node C. And then coming off of node C, we have the inductor and the cap and the resistor in parallel again. And so this over here is node B. So this down here is all node B. So now we have each of these impedances, which is a set of parallel impedances. Okay. So I'm going to just take this here and move that for a minute and save that. All right. So all right. So our total impedance now between A to B is this section here where we have have the inductor of 9 ohms in parallel with a 16 ohm capacitive reactance and a 12 ohm resistance. Okay, so I'm just going to call this here, I'll just kind of label that Z parallel. Okay, so Z parallel. All right, so Z parallel here is equal to 1 over let me scroll this up just a little bit here. So it's equal to 1 over J9 ohms plus 1 over the 12 ohms minus J16 ohms. Okay. So that is my parallel impedance. And so if I go into Octave and calculate that, okay, one of the things we need to remember to do is to use parentheses. Okay, so we need to make sure that we put in all our parentheses on here to get the answer. So looking at that, we see here that I have the parentheses. Yeah, look, so I had parentheses around the J9, and I had parentheses around the 12 minus J16, which is the impedances here. Okay, and so the parallel impedance then of this circuit, it has a resistance value of little more than 5 ohms and a reactance value of plus 11.9. Okay, so that is just for one of these pairs. Okay, so we could kind of redraw the circuit now as basically just kind of maybe being an impedance here. Okay, so we have the node A was blue up here. So here's node A. Just kind of, there's my node A. And here's my node C. And down here is my node B. Okay. All right. And so we're coming out of node A to this impedance, which is that Z parallel impedance. And then we're coming over here to this other one. And then from there, we're going to C. And then from C, we're coming out to B. And from here. So each one of these is this Z11. Or excuse me, it's not Z11, it's Z parallel. I just wrote it as an 11 and thing. So each one of these boxes represent this Z parallel piece, which has this value. Okay, so each one of these boxes have this impedance inside of them. Okay. However, these two are in series. So we can simply just add these two impedances together. So we can add those two together to get the total. To get the total impedance within this circuit, these two are just series, so it's just this total impedance here. But now this total impedance is in parallel with this impedance. So Z total, okay, so the Z total okay, so Z total is this Z parallel in parallel with two of them in series. So that becomes 1 over the Z parallel value plus 1 over two of them. So you could either, do parentheses and you can have the Z parallel plus okay, let me try that again. Z parallel plus another Z parallel. Okay. Or, we could do a little algebra here and just say 2 times the Z parallel. Okay. So if we calculate the parallel of those, we could get Z total. So Z total is 1 over, and again, make sure you use your parentheses. And we'll calculate that. Okay. And so that gives me a total impedance here for this circuit as being the notice the parentheses here. So, all right, so this whole thing, we have 1 over Z11 plus 1 over 2 times Z11. But notice the parentheses. Okay, if you don't have your parentheses correct, now I put parentheses right here, but I could have lived without those. But here where we're doing 2 times Z1, if you don't have the parentheses, you're going to have the wrong answer. All right, so but that gives us a total impedance of 3.3575 plus 7.9585, and the octave program I'm using gives it as an I. Your calculator showed it as I, but we prefer J so we don't confuse it with current. Okay. All right, so that is our total impedance for this circuit, which of course is the total impedance for the original circuit. So just kind of as a reminder here, the original circuit, okay, so all right, the original circuit, I'll try to find some space here for the original circuit. So the original circuit is right here. So this is what the original circuit looked like. Okay. And so what we did is we converted the original Y portion, the Y portion, which was the inductors. Okay. So we took this Y converted it into a delta. Now that delta was in parallel from A to B and from A to C and from C to B. It's in parallel. So these are all each in parallel. And so I calculated those total impedances for each parallel. And then I combined, you see, from going from point A, you could either go through the resistor capacitor branch or the inductor branch and make it to point C. And then at point C, you could either go through the resistor capacitor branch to B, or you could go through the inductance branch to get to B. So each one of those is that parallel combination there of the two delta circuits. Okay. And then that, of course, gives me this total impedance. Okay, so if we were going to put that in Blackboard or on the exam, right, it would be 3.3, but then there's a 7 to the 5, so that would round up to 6. So 3.36 ohms plus, and I just like to put the J here because it doesn't get confused with the units, 7.9, and then the 8 is going to round the 5 up to a 6, so 7.6 ohms. So this is my Z total. Okay. So then, looking at the original circuit, we were supplying a voltage. In the original circuit, we were applying the voltage of 100 volts angle 0. So now that we have a Z total, we can calculate the current, the total current coming in to this circuit using Ohm's law. We get that the current I total, so we get I total is equal to the voltage divided by the impedance. Okay, and so the voltage was 100 volts angle 0 degrees, and Z total here is this value. Okay, so we'll just divide by this Z total. Okay, I'll put it back in the box too so we can refer to it. All right, and so now if we do those calculations, we get that the current I is equal to the voltage, 100 volts, divided by the Z total. Okay. And depending on how you're putting this in here, you need to make sure that you put parentheses around it. Okay. And then since I'm using the Octave software to calculate this, it puts it in rectangular form, and then I need to convert that into to polar form by doing the absolute value and also doing the angle, calculating the angle. And the Octave software, when it calculates the angle, okay, so when it calculates the angle here, it puts the angle in radians, so I have to do 180 divided by pi to convert it to degrees. So the answer is 11.57. All right, so again, the 7 will round the 6 up, so that would give me 11.6 amps at an angle of minus 67.1 degrees. Okay, so that is the total current in polar form for this circuit if it's being supplied by 100 volts. So this was a example of doing a delta to Y conversion, and also doing a reduction method of reducing impedances that are in a series parallel combination and reducing those down into a total impedance. So this was Z total up here. Okay. And this is the total current. Okay.